In this video, we're going to review some basic stoichiometry. So we've got 5 questions to cover. We're going to walk through each one. In the first one, we're going to calculate the molar mass of 2-propanol, which we're told has the chemical formula C3H8O. To determine molar mass, we'll need to use the masses of individual elements from the periodic table. The chemical formula for 2-propanol shows us that we have 3 carbons, and each carbon has a molar mass of 12.01 grams per mole. There are 8 hydrogens in this compound. From the periodic table, each hydrogen has a molar mass of 1.008. And lastly, there's only one oxygen, which has a molar mass of 16.00. What I'm going to do is add each one of these together so that I contribute mass from 3 carbons, 8 hydrogens, and 1 oxygen to the overall molar mass of this compound. Adding all of these together gives me 60.09 grams per mole. In question 2, we're asked to calculate the mass of a 0.250 mole sample of aluminum sulfate. In order to move from moles into mass, we need to use the molar mass as a conversion factor. So we're going to have to first determine the molar mass of aluminum sulfate. For this purpose, there are 2 aluminums, each at 26.98 grams per mole, plus not just 1, but 3 sulfurs, each at 32 grams per mole, and not just 4, but 12 oxygens, each at 16. This amounts to 342.14 grams per mole for the molar mass of aluminum sulfate. That means 1 mole worth of this compound will weigh 342.14 grams. We can use that identity as a conversion factor to move from starting units of moles into target units of grams of aluminum sulfate. To do this, we build our conversion factor to get rid of moles, so moles go in the denominator, and convert into grams, so grams go in the numerator. 1 mole of this substance has a mass of 342.14 grams. Multiply through and keep 3 significant figures, and we end up with 85.5 grams. In question 3, we're asked to determine how many moles worth of oxygen atoms are contained in a 1 mole sample of this chemical compound with formula C18H21NO4. If we've got 1 mole worth of this sample, we can first convert moles of a sample into molecules of our sample. We'll do so using Avogadro's number. Avogadro's number tells us that in 1 mole of anything, there are contained 6.02 times 10 to the 23rd of that thing. In this case, it's molecules. Once we know molecules of our compound, we can use the compound's chemical formula to give us the ratio of atoms of each type in that formula. For example, in 1 molecule of this substance, C18H21NO4, we know that there are 4 atoms of oxygen. Once we know how many total atoms of oxygen are contained in this molecule, we can carry out a final step to convert atoms back into moles. We'll use the same relationship between moles and Avogadro's number that we used before. We can move between mole counts and absolute counts using 6.02 times 10 to the 23rd. And what we'll notice here is that because we converted from moles to molecules in step 1 using Avogadro's number, and then from atoms back to moles, again using Avogadro's number in step 3. that Avogadro's number just cancels out. In the first step, we multiplied by it. In the last step, we divided by it. So there was really no need to use Avogadro's number in the first place. We end up with 4 moles worth of oxygen atoms per every mole worth of our chemical formula. The major takeaway from this example is that chemical formulas give us mole ratios of atoms that make up a compound. So let's use that same principle to answer question 4. In question 4, we're given information about a 0.25 mole sample of aluminum sulfate. We'd like to know how many moles worth of sulfur atoms are contained. We can use the chemical formula now directly to move from moles of a molecule into moles of a component atom in that molecule. So all I have to do in order to perform this conversion is recognize that in every 1 mole worth of aluminum sulfate, there are 3 moles worth of sulfur atoms. In the same way that in every 1 molecule of aluminum sulfate, there are 3 atoms of sulfur, or in the same way that in every dozen molecules of aluminum sulfate, there are 3 dozen sulfur atoms. In any case, there are 3 moles, or 3 atoms, or 3 dozen sulfurs for every 1 mole, or molecule, or dozen aluminum sulfates. Therefore, in a quarter of a mole, 0.25 moles worth of aluminum sulfate, we must have 0.750 moles worth of sulfur atoms. So on to our last example. We'd like to know how many molecules of ethanol are contained in 1 drop of the substance, given that 1 drop has a mass of 0.0430 grams. So again, because we're interested in mass, we're going to need to use the molar mass of this substance. The molar mass of ethanol comes from 2 carbons, each with a mass of 12.01 grams per mole, plus 6 hydrogens, each at 1.008, plus 1 oxygen, 16.00, for a total molar mass of 46.07 grams per mole. Why do we need to know this? Because in order to go from mass into count of molecules, we need to go through moles. When in doubt, convert to moles. We'll need to first convert the mass of 0.0430 grams into moles, and then move from moles into a count of molecules. So grams to moles, moles to molecules. We can accomplish the first step using molar masses, and the second step using Avogadro's number. So we're going to put the 2 concepts together in this problem. 0.0430 grams gets converted into moles by canceling out grams and using the molar mass that says every 1 mole worth of this substance has a mass of 46.07 grams. We convert what is now moles into molecules by recognizing that every 1 mole contains 6.02 times 10 to the 23rd amount of stuff. Again, in this case, it's molecules. Now, grams cancel, moles cancel. We'll be left with molecules in our final answer. 0.0430 divided by 46.07, then multiplied by 6.02 times 10 to the 23rd, results in 5.62 times 10 to the 20th molecules of ethanol.